So second derivative is 2.5. You can call this C. Second derivative of implicit differentiation. Implicit differentiation. Second derivatives with implicit differentiation. So a second derivative, like I mentioned, there is no limit to the number of derivatives you can do on an equation. There is no limit. There is no limit to the number of times you can take a derivative. You can take a derivative. Functionally, there's no limit, right? So if I have, for example, the example I gave before, y equals x to the third power, right? If I do the derivative, I'm going to get dy dx is 3x to the second power. Let me do this in colors. Do the derivative. I get 3x squared. If I do the derivative again, the way we would write the second derivative is d squared y over dx squared. And that would equal 6x. So that's the second derivative. This is the first derivative. Let me do it like this. First derivative. Second derivative. If I do the derivative again, I would get d cubed y over dx cubed. And that would be just a 6. And there's no reason I need to stop there. I could keep going. I mean, the derivative after that would be a 0, but you get the idea, right? So I have my first, my second derivative. This is the third derivative. No limit, right? But this language here of the squared, dx squared, dy squared, d cubed, it's kind of like this this terminology is very like cumbersome. It's a lot of like cubes and writing. Is there an easier way? It'd be nice if there was a better way to write the first, second, or third derivative, a more like concise version of these things, instead of having to write these squares and these cubes or whatever, right? It'd be better to have some different symbology. And we have another way we write derivatives, a sort of shorthand for derivatives. Instead of dy dx, the way we write this oftentimes is y prime. Let me just do the right y prime. Y prime, this is y prime, means derivative, means dy dx. So we have a shorthand way of writing a derivative. We say y prime instead of saying dy dx. It's not a 1. That's like a quotation mark. This little symbol here is not a 1. It's like a little hash mark, like a quote symbol. It's a little tally mark. It's not a number. It's just like a little apostrophe. So if y prime, right, that's the first derivative. The second derivative, we can say this is y double prime. Y double prime. Or the second derivative. And the third derivative, we just say y triple prime. So these are those shorthand ways to describe the first, second, third, really any derivative we have ways to describe this derivative by this little like tally mark. Just makes it a little easier to identify. Instead of writing all this dy cubed, d squared, whatever, all this stuff, we have this little symbology here where we write it like that. Yeah, infinite prime. If you want to get into a bunch of crazy math, there is a lot of study about, well, what if, which types of functions are you able to do derivatives of, and different families of functions, and how far can you go with derivatives? Like, again, like I said, with this polynomial equation, the derivative of polynomials always go to 0. The derivative of e to the x always is e to the x. The derivative of sine has this cyclical formation. Other functions, like the square root function, the square root of x, has another different kind of process that it goes through. And so there's a lot of interesting studies about families of functions and their derivatives and what happens as you take a derivative over and over again of an equation. But that's for another time. If you're interested in that, study math in college. It's fascinating. Don't get me wrong, but, you know, baby steps first. So we have this derivative process, right? A different symbology here. Y prime. Easier to write. So we're going to use, I'm going to start to use this prime symbology just because it's like, again, mathematicians, I've said this before, mathematicians are lazy. We are lazy people. I want to write as few symbols as possible. So instead of dy dx, I'm going to write y prime. Instead of d squared dy, I'm going to write y double prime, right? So I'm going to use these symbols because I'm a lazy mathematician. That's what we do. So let's get into finding, so now that we have this symbology, we're going to find a second derivative of an implicit differentiation. So find the second derivative, which is dy dx d squared y dx squared, or y double prime, of the implicit equation, implicit function. So we're going to do this with just x squared plus y squared equals 4. Find the second derivative, d squared y over dx squared, or y double prime, of the implicit function here. And the steps we're going to take, the first few steps are going to be the same. 1, d dx everything, the whole equation. 2, we're going to isolate dy dx, which we're going to call y prime. Okay. And then 3, we're going to do d dx again. So we're going to do the derivative regular. We're going to find the derivative of the whole thing, isolate the dy dx, and then we're going to take the derivative again. And the last step is substitute for dy dx, or y prime, from right here. So we're going to, in the second derivative equation, in d squared, I guess I should say for isolate y double prime, and then number 5, do the substitution. I guess it doesn't really matter the order, but we'll do it this way. So in the second derivative, the point is in the second derivative, you're going to see dy dx come back again. And then you're going to need to, like a substitution, take the dy equation that you got from number 2, take the equation, and plug it in to the second derivative equation. And I'll show you what that looks like in this problem here. Okay, so here we have our equation. This is an equation of a circle. You can see x squared plus y squared equals 4. And we're going to do the derivative of this whole thing, d dx of this whole thing. So we're going to get 2x plus 2y y prime equals 4. And see, this is why y prime is very useful, right? So we see every time there's a y, there's a dy dx, which I just write as y prime, and it cleans up the little process. It cleans up the equation. Right, this y prime is the same as dy dx. It's just a, simpler way to say it. Just like before, every time there's a y, every time I do the derivative of a y, it's going to turn into a y prime. So here's this equation here. We're going to isolate this y prime, same way we did before. We're going to minus the 2x on both sides. Oh, equals, not equals 4. Equals 0, everybody. Derivative of 4 is 0. Minus 2x on both sides. 2y y prime equals negative 2x. Divide by 2y, divide by 2y. That cancels. And we have y prime equals negative x over negative y. Negative x over y. Because the 2's can cancel. 2's cancel. I have negative x over negative y. Great. No problem. I'll give you a moment to write that down. So we found our first derivative, or y prime. Again, not a 1, just like a little quote mark. Yeah, sure. So again, right here, the way we have this y prime is, just like I said, every time you do the derivative of a y, it becomes a dy dx. But instead of writing dy dx, I'm just using the symbology of the y prime. Just because it's cleaner, it's like, I don't know, it just makes it less writing, really, is all it does. It's just less writing to write. Y prime, and it helps to keep track of like where the y's are. You need to, the reason we use the prime symbol is because, again, that's not a 1, but even with 1s, we don't really generally write the 1. So you're not going to confuse it for like an exponent. It's just a prime. There's our derivative y prime. If you really prefer the dy dx symbology, you can continue to use that. Yeah, it's exactly the same as dy dx. If you prefer this, you can keep using dy dx. There's no wrong way to do it. I just wanted to show you another way to write it because it might save some time. Yeah, it's the same as dy dx. So now that we got the dy dx alone, right, y prime, right, here's our derivative. This is our first derivative. First derivative. We're going to have to remember that. We're going to do the derivative again. We want the second derivative. We do our derivative again. And the derivative of y prime is going to become y double prime, which is the same thing as d squared y over dx squared, right? Y double prime is the same as that. Let me write this smaller up here so I don't get confusing. Right? Y double prime is the same as d squared y over dx squared, right? That's what the double prime is. So that's our second derivative. That's what we're looking for. So the derivative of y prime is y double prime, which is the same as this symbol here, but just simpler, right? More precise. So I've got my y double prime. It's isolated already, which is nice. Now I have to do the derivative of this side over here on the right. I need the derivative of this. And this, clearly, I need to use a quotient rule, low d high minus high d low over low squared, because I've got my situation here. So I'm going to go low d high. It's going to have a quotient rule, low, which is y. D high, the derivative of negative x is negative 1. Low d high. Minus high d low. High is negative x. The derivative of the bottom here is y prime, or dy dx, the derivative of the y. So low d high, minus high d low, the derivative of y is y prime. Low d high minus high d low over low squared over y squared. Okay? And what we're going to do now to finalize this, because we don't want to keep y prime in this equation. I want only to be involving x and y by itself, no y primes. So I'm going to have to substitute y prime, right? So I'm going to take this equation here, which is y prime, and plug it in to y prime there. I'm going to take this y prime equation here and plug it into the y prime right there. I'm going to substitute, because I only want x and y. I don't want y prime. So I see y prime. I got to plug my equation into y prime. So let's simplify this. Y double prime is equal to negative y minus plus x times negative x over y squared. Okay? Plugged in the y prime. We could simplify this a little bit more. Let me go over here maybe. So I can keep going a little simplifying, right? This x times negative x over y, this is like x over 1. So this becomes negative y plus, minus, I guess, x squared over y squared. And again, I don't really like the fraction over a fraction stuff, so if I make this over 1, multiply both of these by a y on the top and the bottom, I'm going to get negative y squared minus x squared over y squared. This y then goes in the denominator, so that's my denominator y. So it becomes y double prime is negative, I'm going to rearrange this, x squared minus y squared. Oh, actually, I don't think I, no, let's keep it the same. Hold on. Negative y squared minus x squared over y cubed. That would be our second derivative. Let me move the denominator to the denominator. Here I just combined these top ones together into one fraction, and then put my denominator on the bottom. So simplifying a little bit, right? Using a little bit of algebra rules, simplifying, rearranging fractions, all that stuff, gets us to this equation here, which is our second derivative equation. Yes, Lizette, I made the top two fractions have the same denominator, right? So I gave them both the denominator of y. This had a denominator of y. I needed this to be the same so I could combine them together into one fraction so that I could move this bottom part to the bottom here. Exactly. Any other questions about this process? So that's our second derivative of that equation. That's interesting. Oh, that's fine. Should we try it one more time? Let's try this again. A little bit more complex example, perhaps. Oop. Find y double prime of the equation. Let's go xy no, let's do this. Hold on. 3xy minus 4 cosine x equals negative 6. Three xy minus 4 cosine x equals negative 6. Find the second derivative of this implicit equation. We start the same way. We find the derivative, right? We ddx the whole thing, get our equation, find our derivative. And again, we have to use whatever rules we need to solve each problem. So this part here, this 3xy, I'm going to need my product rule. First times derivative of the second plus the second times the derivative of the first. 5 steps up here. ddx the whole thing, isolate the y prime, derivative again. Y prime should already be isolated, but if you need to, isolate y prime again, y double prime, and then substitute and simplify. So derivative, isolate, derivative again, and then solve and substitute for the y prime. Okay?
So let's do that. Let's follow the steps. So first step is do the derivative. d dx this whole thing. Product rule says I do first times derivative of the second. So this is going to be 3x y prime. First times derivative of the second, right? The 3x times the y prime, derivative of y. Right? Much easier to write, y prime. First times the second plus the second times the derivative of the first. The second is a y. The derivative of 3x is 3, so it's 3y. And if you want to put parentheses around that to kind of like isolate it, you can. Keep that as like, that's the derivative. These two pieces here are the derivative of this equation here. Right, these two pieces. Minus my derivative of this for cosine x. Well, the derivative of cosine is negative sine, so minus makes this a plus for sine x equals 0. So we've got to get the y prime now. We did the derivative. Got to get the y prime by itself. So I'm going to move this 3y. I'm going to move this negative, this 4 sine x minus the 4 sine x. Move those away. 3xy prime equals negative 3y minus 4 sine x. Then divide by 3x to cancel that. Y prime is negative 3y minus 4 sine x over 3x. And there's my first derivative. So first, find the first derivative, step 1. Do d dx, isolate the y prime, get y prime by itself. Yes, use the product rule. Yes, I use the product rule for the 3xy. Right, this first 3x times the derivative of the second, the y is y prime. Right, derivative of y is y prime. Plus, right, first times the second plus second, the y, kept the y, times the derivative of the first. The derivative of 3x is just 3. So if you like, I can do, this is like, this is f, and this is g. So this is f g prime plus g f prime. Little product rule. All right, once we have all of that, we find our derivative again. We do the second derivative. And again, looking at this, it's going to be a little bit of a messy quotient rule going on here. But that's okay. We'll just, we'll deal with it. Derivative, second derivative, we got y double prime. Right, the derivative of y prime is y double prime, second derivative. Equals, let's do our quotient rule, low d high minus high d low over low squared. So again, I've got low d high f over g. So I've got low d high fg prime. Gf prime, I should say. Low is 3x. The derivative of this upper part, so the derivative of negative, I just do this in two pieces. The derivative of the 3y and then the derivative of this, it's going to be one like equation part.
The derivative of negative 3y is negative 3y prime. My chain rule says that the derivative of the y without an exponent, just the y falls away. And I get the negative 3 part. And then the derivative of the y is the y prime. So derivative of negative 3y is negative 3y prime. Minus the derivative of 4 sine of x. 4 stays. The derivative of sine is cosine. So that's g f prime. Low d high. Minus high d low. So I keep the upper part now the same. The upper part is going to be negative 3y minus 4 sine x. Right, that's high. D low, the derivative of the low part, is the derivative of 3x is just a 3 over 3x squared. So now we've got everything here. The only piece that we need to work out is we have this y prime right here. So I need to take all of this stuff, this whole big messy equation, and put it inside of the y prime right there. It's going to be messy. It's going to have all kinds of weird actions. It's okay. You're big boys and girls now. You're big boys and girls. You're big math people. You can deal with all the messiness. It's okay. Right? Just like cleaning up your room. You've had to do that for many years. Same situation. Whoopsies. Clean up your room, everybody. Well, sure. I mean, if you just left the y prime alone, no. We need to put the y prime in because we want to get x and y so we can solve it, various things. I mean, you don't leave it alone. Substitute. So 3x times negative 3 times negative 3y minus 4 sine x over 3x minus 4 cosine x minus all this stuff here. I'm going to take this 3 actually, and I'm going to do a little bit of simplifying here. I'm going to distribute this 3, make my life a little easier, minus negative 9y minus 12 sine x over, I guess I could do 9x squared. I don't know. Yeah, you can distribute all the time. I could even distribute this, and I'm probably going to eventually distribute this 3x. Right? Yeah, you can distribute anytime there's a multiplication with a parentheses like this. Distribution happens all the time. Okay, are we done? Technically, yes. This is the correct answer. If you were doing this on a free response question, this is fine. You may need to then plug in for x and y, but, you know, this is fine. You're correct. We like to see if we can simplify a little bit more, though, right? We like to simplify. We like to adjust. So we're going to do a little bit more distribution, like, for example, this -3 here and this 3x on the bottom. If I were to multiply, this -3 can cancel with that one there, and I just have to distribute the negative sign inside. So if I do that, oops, I mean, now we're just, this is all just extra, bonus, y double prime. Let's do it. We've got 3x on the outside here. I've got 3y plus 4 sine x over x, 3y. And then this is minus 4 cosine x. I'm going to distribute this negative as well, just to distribute the negative sign. So I get plus 9y plus 12 sine y, sine x. And now I want to distribute this 3x as well. What if I did this over 9x squared? Right? Distribute that 3x. So let's see. What can I do here? 3x times 3y plus 4 sine x minus 12x cosine x, this is over x, plus 9y plus 12 sine y, sine x, over 9x squared. Okay, a little bit more. This x here and this x here can cancel. And then I distribute that 3 inside. So I'm just really, I'm eliminating pieces left and right. So 9y plus 12 sine x minus 12x cosine x plus 9y plus 12 sine x. Look what's happening here, everybody. 9x squared. I got some like terms. 9y, 9y. 12 sine x, 12 sine x. Look at all this crazy things we can do. 9 plus 9 is 18y. 12 plus 12 is 24 sine x minus 12x cosine x over 9x squared. And that's our double derivative. I'm going to zoom out so you can see it all. Oopsies, too much. There, how's that? After we substituted what we did, my process there. Again, we were satisfied at this point here. This is fine. This is fine. Once you plugged in the y prime, what you had there is fine. Right? We were done essentially at that point. All of this other stuff, and the reason why I like to do this process of simplifying, the reason I think this is valuable to try simplifying, it's valuable because you will need to do this. Maybe not this quite as complicated, but it's good practice. You will need to simplify things like this for the AP test, because in the multiple choice section, for example, they'll give you answers and it may not look like what you have. And so being able to see, oh, that gets canceled with that, and that becomes this, and then they move this fraction down here, and these two got combined. Being able to see all this process will be helpful on that AP test, on various things like that. It's, again, not going to be this complicated, but the practice, the process of being able to see how this all gets manipulated will be helpful. That's what practice is for, Angel. We'll get you all primed for it as it gets closer. And what you'll notice is that there's certain tricks they use, there's certain little details, and the more you practice those, the more you see those, the easier it's going to get. All right, I got about 10 more minutes. I did want to show you one more example. Not of the second derivative, of now I want to find a tangent equation. So you got 3 questions on the homework of doing the second derivative. Rearrange as much as you feel comfortable with. Again, trying the rearrangement is helpful. It's especially helpful since you have the answers in the back of the book. See how you get there, right? Get your answer, see what they got, and try to get where they get to. That's the process of simplifying. See if you can find out how to get there. It's like a puzzle. I mean, that's what math is like. It's all a puzzle. Yes, Lizette Garcia. What is your question? Y double prime? Uh-huh. Mm-hmm. Sure. Well, so what I did here is what I ended up distributing wasn't the -3. Because what I noticed here, I noticed that this 3 is it's like a 3 over 1, right? I notice I have a 3 up on top here. I also notice I have a 3 down below. And so this 3 down below canceled with the 3 here. And really what I'm distributing is -1. Maybe I didn't make that clear enough. Yeah, this -3, the 3 canceled with the 3 down below. And really what I ended up distributing was -1. That's why this became positive here, and why the 3's disappeared. If you do distribute the 3, you'll get 9 and 12, and then you'll have the 3 down here, but then you can factor out the 3 cancel. It's just, it's easier to see it already canceled out front here, out front there. And it's similar to what I did right here. Similar down here, right? I saw this 3x in front. Well, the x down here, when I distributed this 3x thing, I didn't do it to each of these up on top here at first. I just kind of put it in front. I just put this 3x sort of in front of this big parenthesis here because I saw that this x could cancel with the x that was down below here. And then I ended up distributing just the 3 part, getting my 9 and 12, and the x went away. This 3x did have to multiply this 4 cosine, though. That's where the 12x came from. But that's the little, right? Those are the kinds of, seeing those details, seeing those tricks, right? Noticing, oh, there's x here, there's x there. Looking for those kinds of patterns, right? Oh, I'm going to be able to cancel this x with this x here probably. If it's on the top and this is on the bottom, those are going to cancel. So maybe I just need to do the 3, but don't cancel it for the second one. It needed to be here. That's why I didn't cancel it here. I had to do it in the middle here. Now, are there other questions like that about how I got certain pieces, where they came from? So your assignment, again, you have 3 of these to try on your own over the weekend. And again, looking at the back of the book, seeing what answer you get, try to get where they got. Try to get that same, see how you can manipulate, rearrange to get that same process. It's only because of years of practice, Pariso. Only because I've been doing this a long time. You get to see see the future in that way. After however many years I've been doing this, 14 years of teaching, your eyes will get pretty good too. So, all right. The last thing I want to show you is how to find a tangent equation. This is going to be quick. There's, I think, 2 questions on this, tangent equations. And it does not involve the second derivative. This is only the first derivative. Tangent equations only involve the first derivative. So, example. Find a tangent equation This involves only the first derivative, find the slope, find the equation, right? When I say tangent equation, immediately your brain should go to y equals mx plus b. And you're going to note that you need the slope, need m, and you're going to need b. M comes from dy dx, or y prime. B comes from the xy coordinate that you plug in. So we're going to take an equation here. We're going to say, what's a good one? I'm just going to use a derivative I already found because it's easier. X squared plus y squared equals 4, right? We already did this one. I ddx the whole thing. And we get y prime was equal to negative x over y. I'm not going to re-go through that process, but we just found y prime, right? Oh, I should say at what point? Oh, this is messy. Let's see. What did I say? Like root 2 comma 1 over root 2. No, root 2 comma root 2. Root 2 comma root 2. There you go. Finding the tangent equation at that particular point, right there. Root 2 over root 2. Root 2 comma root 2. So we got the derivative, right? This, oh shoot. This derivative is our slope. This is our slope. And so the steps, you can think of the steps of this process. Let me write down the steps here. Finding a tangent line. 1, find y prime. Plug in x, y for the slope. Part 3. Use y equals mx plus b and plug in x, y for b. So we found y prime. I'm going to plug in x and y. This means I'm going to get the slope equal to negative square root 2 over square root 2, which is equal to negative 1. So that's my m. Got y equals negative 1 x plus b for my tangent equation. Y equals mx plus b. I'm going to plug in the root 2 root 2. I get square root 2 equals negative 1 times square root 2 plus b, and just solve for the b. So this is root 2 equals negative root 2 plus b. Add root 2 to both sides. I'm going to get b equals 2 radical 2. So my equation is y equals negative 1x plus 2 root 2. That's my tangent equation. We've done this a few times before, right? We found tangent equations. It's the same process that we use. You find the derivative. You plug in the points for the derivative. You get the slope. Use that slope, plug in the points again. Find the b, get your equation. So you have a couple of questions. I want you to find the tangent lines using this implicit differentiation process. All right, folks, the homework is up on Schoology. It's same section. I think it's 49 to 57 odd. 5 questions for you. Try those over the weekend. One thing I want to mention, so we're done, but before we go, the last thing I want to say is that I will not be here for all of next week. There's something going on. I need to be gone for all of next week. So you'll have a sub next week. We will meet Monday, Tuesday, Thursday next week. So while I am gone, what you will be doing, you catch up with your work, but we will be taking the Renaissance test during that time. All week I will be gone. Yes, Manuel, I will be gone all week. I've missed a few days here and there, but I'll be gone all week next week. So you'll be doing the Schoology test on Schoology, and I may leave some videos for you and some Khan Academies for you to practice, things like that. We'll pick back up things when we get back the week after next. Pick up how to use derivatives in our equations. But I'm going to leave you with some practices, some reviews, like catch up on any missing work, catch up on the stuff. I'm going to leave some videos like I mentioned last time, some videos about different types of derivatives that you can review just to really get yourself practiced and knowing how to do this. So take that time, catch up, take that Renaissance test, do those Khan Academies, things like that. All right, everyone? I'll be available by message. You can message me. But yes, in the chat, type goodbye. Once you type goodbye, you're free to go. Thank you all very much. And I will see you in a couple weeks.